Okay, this short video is going to talk about the free body diagram and what it really means, and physically what it's doing. Okay, this is free body diagrams for a rigid particle, which is the easier one. I'm hoping that if you see this video and you can apply the concepts to it, when we get into free body diagrams of a rigid body later on in the course, it'll make a lot more sense. You'll have this grounding. All right, let's take, for example, this ring here. It's a steel key ring that I've put 3 ropes to. 2 of them are, attached to nails on the wall, and one of them is just dangling freely right now, the one on the bottom. So it's actually got no force in it. You can see it's hanging down such that the top ropes are taut, and the bottom one is still free. Now, if we were to think about what's going on here, well, it's really just the weight of that ring that is being resisted by these 2 top ropes. And they're connected to nails on either side in such a way that this is the orientation that this wanted to sit in and stop moving. So this is its point of static equilibrium. So this is like the statics problem you're given. Okay? You can see it found its way down until it found the spot where the force is all equilibrated. So if we cut a free body here, we'd have just the ring, and then we'd have the tensions in the 2 ropes. The bottom rope wouldn't have any tension. It would be 0 right now. Okay? An interesting thing about ropes, they're the simplest of all the statics structures because they can only hold tension. They can't hold compression. You can't push a rope, and you can't really even push them side to side. They really only want to go taut and have tension in them. So we know the orientation of the internal force vector, so we can draw the free body diagram. And when we draw the free body diagram, we like to talk about making cuts. Now, we don't actually come in here and make a cut, because if we did, disastrous things would happen. For instance, I don't want to cut this because I took all the time to tie it up, but what I could do is just remove it from the nail over here. If I made the cut here on the right hand side, it would be the same as this happening. Obviously, it was no longer in static equilibrium. The forces didn't equilibrate, and everything went south, literally. All right, so that's not what we want to do with a free body. When we say make a cut, we're talking about making a fictitious cut. Okay, there we go. When we're talking about making a cut, we're talking about making a fictitious cut. If we were to cut through all of these, we'd need to replace them with the forces that they have inside of them, so that if we made this cut and put those forces on it, the exact forces that are in these cables, the ring would stay still, it would be hovering in air. So it would be like me cutting through the rope and then immediately grabbing it and holding it in place. Because I would be replacing that force that was let go with, my force of my hand, which would be, putting that tension into that rope. So that's what we do when we make a fictitious cut. So if we were to make a free body diagram of this ring right here, we'd have just the 2 ropes, like I said before, with the tension forces that are in them. The bottom one would have 0. And the free body diagram would look something like this. Okay, now, what would happen if we had tension in all 3 ropes? So if I were to hang a weight from the bottom rope, it would start having a tension, right? It would start pulling down. You can see if I pull down, what's happening? It's actually changing the location of the ring. The ring is leaving static equilibrium until it finds a new equilibrium, such that all the forces are equilibrated. So now I've got tension in the bottom rope and tension in the top 2 ropes at different angles. And that's why the angles are so important in these kind of problems. So let me go ahead and put a permanent weight on there. So I'm just going to hang a heavy mass from the bottom. And there we go. So if I wanted to analyze that, I could. I now can figure out what angle I have on the wall for this rope and for this rope. This one here, since it's a weight, we know it's hanging vertically down. I can draw that free body diagram and I can analyze it. If I were to release the rope, any of the ropes here, obviously things would happen. If I were to cut the bottom rope, the weight would fall, the ring would go back up to the orientation it was before. right? Because then it would just be the weight of the ring. If I were to cut it over here, the ring would swing to the left. If I were to cut it here, the ring would swing to the right. So obviously we're not really truly cutting it, but when we talk about making a cut, we always want to cut through members, because then what happens is when we draw the free body diagram, we have to draw those internal force vectors, and that's what we're looking for. So this is what the free body diagram for this would look like, and if you went on to solve it, this would be your answer. Now, you can see when these two ropes have tension force, there's forces in the X. Even though all I'm doing is hanging a weight from the bottom string, which is a Y direction force, I'm generating X direction components of force. And that's to be expected. So the X component of this cable has to fight directly the X component of this cable, because the weight is not even involved in the X direction. So those two have to equilibrate each other. And then together their two Y components have to resist the total weight hanging down, which in this case is the weight below. So that's it. I hope this was helpful in showing you what free body diagrams really represent.